guys, this is Miss Bufford, and in this video we're going to talk about writing balanced ionic formulas. So your learning goals here are to be able to explain the meaning of all the letters and numbers in a chemical formula, be able to correctly write the formulas of ionic compounds, including those with transition metals or polyatomic ions, and be able to identify polyatomic ions, and be able to distinguish ionic, covalent, and metallic compounds from each other. So we're going to go ahead and start out by talking about how to determine what the charge on any given ion is, because ionic bonding is about how ions come together and form compounds. And in order to figure out what their balanced formulas are, you have to understand where their charges are coming from. So we've talked a little bit about this already this year, and we know that metals, they lose valence electrons, and non-metals, they gain electrons in their valence shells. And so let's go ahead and we're just going to focus on, the main group elements here. Group 1 elements, the alkali metals, they have one valence electron and they're metals with low electronegativity. So they're going to end up losing their one valence electron in a chemical reaction. When they lose their one valence electron, remember, they're losing some of their negative charge in that electron cloud, which is balancing out the positive charge from the nucleus. And so when they lose that negative charge, they're going to have a net positive charge. So all of the group 1 elements are going to have +1 charges when they are ions. All right, they all lose that one valence electron. Group 2 elements, or these metals, they're going to lose 2 valence electrons, and so they're going to end up with an overall +2 charge. Group 3 metals, so here starting with aluminum, are going to lose their 3 valence electrons, and they're going to form +3 ions for the most part. All right? Then starting on the opposite end of the periodic table, these don't really gain or lose. Remember the noble gases, so we're not going to talk about those, but we're going to talk about the halogens. These halogens, remember, they have really high electronegativities. They're really good at attracting electrons in towards themselves, and they have 7 valence electrons, the halogens do. And in order to fulfill the octet rule, which says that they all have to have, or they're all trying to have 8 valence electrons, they're going to need to gain 1 more electron. And so remember when we drew the Lewis structures for these, so we'll do fluorine down here. Remember they have 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. They have this 1 electron over here that's by itself. And so what fluorine it tends to do, and the elements in its family, they tend to gain 1 more electron from something else. And when they do that, they become -1 ions. So they have a -1 charge. All right, then oxygen's family over here. Here's oxygen's Lewis dot structure, 1, 2, 3, 4, 5, 6. Remember they have 6 valence electrons. They're in group 6A. They have 2 places where they can, gain electrons. So they tend to gain 2 more electrons to fill that outer shell. And when they gain those 2 electrons, they become -2 ions. All right, so that's oxygen's family. And then nitrogen's family, let's draw nitrogen's Lewis dot structure. 1, 2, 3, 4, 5 valence electrons. You can see they have 3 places where they can gain electrons in order to have 8 valence electrons in their outer shell. And when they gain those 3 electrons, remember they're gaining negative charge, and so they're going to have -3 charges. Right, so all the nonmetals here in nitrogen's family are going to form -3 ions. Oxygen's family, all those nonmetals are going to form -2 ions. And then fluorine's family are going to all form -1 ions. Now, carbon and silicone don't tend to form ions. They don't participate in ionic bonding, because they're kind of at that sweet spot right there in the middle where they've got 4 valence electrons, so they're not really going to lose valence electrons because their electronegativities are relatively high, and they're not so they're not going to lose. They do share electrons, and we'll talk more about that when we get to covalent bonding. So carbon and silicone, we're not going to worry about giving them charges. And then don't worry too much about boron. We'll talk about boron later on, but you don't have to worry too much. So really what you need to know is that group 1 metals form +1 ions, group 2 metals form +2 ions, group 3 metals form +3 ions, and then group 7 nonmetals form -1 ions. Oxygen's family of nonmetals forms -2 ions, and the nonmetals in nitrogen's family form -3 ions. So if you got that, you'll be good for determining charges. Now, we're also going to talk later on about how to determine charges for these transition metals. It's not something you can do just by looking at their placement on the periodic table. You have to actually look at, what they're in a compound with, or what their name is telling you that the charge on that is. All right. So let's go ahead and talk about the parts of a chemical formula now. So we've got first the coefficient, and this tells you how many units or molecules you have. So how many of these groups of atoms you have. The chemical symbol tells you what elements are involved, and these are always going to be listed in order of decreasing metallic character. So the least metallic, the most metallic element goes first, and if it's a metal, that's great. If it's a non-metal, it's just the one that's closest to the metals is going to be written first, and then the non-metals or the least metallic elements are always going to be written second. And then the subscript, these little numbers right down here, tells you how many of each type of atom there are in that formula. And if there is no subscript after the element symbol, for example, for magnesium, there's no subscript there, that's just understood that we have one magnesium atom. So we only write subscripts if there are more than one of each type of atom in a formula. All right, so because ionic substances, they're not molecules. And so because of that repeating pattern of positive and negative charges in an ionic substance, no true molecules are formed. Therefore, when discussing ionic substances and their formulas, we're going to use the term formula unit. And a formula unit is the smallest whole number ratio of atoms that make up an ionic substance. For example, in sodium chloride, the sodium atom, which is a group 1 atom, it forms a +1 charge because it loses one valence electron. And the chlorine atom, which is a chlorine atom, remember that's a group 7 element, it needs one valence electron to fill its shell. They're going to come together in a 1-to-1 ratio because sodium's getting rid of one electron, chlorine is gaining one electron, and they're making each other happy. All right, and so that's going to be a 1-to-1 ratio where there's one sodium atom for every chlorine atom. But in other compounds, in lithium oxide, for example, lithium can only give up one electron. It's a group 1 element. But oxygen, it needs to gain 2 electrons, right? Because it's only got 6 valence electrons. It needs to have 8. And so in order for that to happen, it has to pull in 2 electrons. And so 2 lithium atoms are going to be required to satisfy the need for oxygen to have those 2 electrons. And so these are going to combine in a 2-to-1 ratio. So where we've got 2 lithium atoms for every 1 oxygen atom. And so when we're writing these balanced formulas, we have to consider what the charges on the ions are, and we have to write them in a balanced way. So let's go ahead and talk about how to do that. I'm going to show you 2 different methods for doing this. And my reasoning here is that if I go ahead and I just show you the quick and easy way to do this, then I confuse a lot of people who aren't sure why that works. And so I'm going to show you, how to balance them the long way, and then I'm going to show you how to do it a quick and easy way so that hopefully you can kind of get a well-rounded understanding. So let's say I want to know the formula for how aluminum and oxygen are going to be combining. And the first thing I want to do is I'm going to list the elements in order of decreasing metallic character. So I'm going to write my metal first and then my non-metal. And I want to write down their charges as well. And so aluminum is a group 3 metal. It's going to form a +3 ion. And oxygen is a group 6 nonmetal. It's going to form a -2 ion. Now, what I want to do now is I want to add these charges up and see if they balance out. My goal here is to get these to equal 0 when I add the charges. And if I add them how they are right now, I end up with a +1. So if I need to try to balance this, let's go ahead and add another oxygen and see if I can get that to balance then. So if I just do this, then I end up with total of +3 positive charges and 4 negative charges. That's not going to equal 0 when I add them together. If I add another aluminum, it's not going to be quite balanced just yet. But if I add one more oxygen, then I end up with a total of 6 positive charges if I add up all the aluminums, and a total of 6 negative charges if I add up all the oxygens, and that gives me a total net charge of 0. So I want to continue to add atoms to either side until I reach a point at which the charges, when they're all added together, equal 0. And so what this is telling me is that it's going to take 2 aluminum atoms and 3 oxygen atoms to neutralize the charge between those ions in that compound, okay? And so the smallest whole number ratio that describes aluminum oxide is Al2O3. All right, so now let's take a look at the quick and easy way to do this. So here's method 2. It's called the crisscross method, and sometimes I like to call this magic because it kind of feels like magic. But let's say, again, we want to know the formula for how aluminum and oxygen are going to combine. And what I'm going to do first is I'm just going to list the elements in order of decreasing metallic character. Then I'm going to include their charges. And the next thing is I'm going to drop the signs. So I'm going to take away the positive and negative sign. And then I'm going to crisscross the numbers. And what this means is that I'm going to literally crisscross these numbers and kind of switch partners and make them subscripts, okay? And this is telling me here's my formula, alumina and Al2O3. It's the same formula we got on the previous page. And so I feel like giving you both explanations gives you, the background of why this works, and then you get the crisscross method that makes this quick and easy for you when you're trying to do the work in your quizzes and stuff like that. All right, so one other thing that I want to point out that's really important is that because formula units always need to be written in the smallest whole number ratio, you will at some point run into a situation where you have to reduce the numbers. And so you can go ahead and crisscross them, or if you can recognize that a charge on one ion is equal but opposite in charge to the charge on the other ion, then you can just cancel them out. If they cancel each other out already, then just go ahead and write your formula. That's a 1-to-1 ratio there, all right? So reduce them if possible. All right, so ionic compounds can also contain things called polyatomic ions. And polyatomic ions are groups of atoms that are chemically bonded together and have a charge. And so here's a list of the polyatomic ions that we are going to use in our class this year. These are basically what a polyatomic ion is just, like I said, a group of atoms that's chemically bonded, and they behave like single particles in chemical reactions. So it's a group of atoms that all stays together while everything else around them is rearranging, okay? So you can treat them like a single independent particle. You need to be very familiar with this list right here of polyatomic ions. One, because you're going to have to eventually get to a point where you can look at a chemical formula and say that definitely contains a polyatomic ion, and you need to be able to show me which part of that formula is the polyatomic ion. And you need to be familiar with their names, because there are lots of times when you're going to see the name, and I can't tell you how many times I've had students call me over in the middle of a test and tell me that they can't find hydroxide on the periodic table. Not just hydroxide, but that's, seems to be a pretty common example. So if you're ever in doubt about whether something is a polyatomic ion or an element on the periodic table, then you always check your polyatomic ion list first so that you don't spend so much time looking through your periodic table to find something that's not there. All right, this is much shorter and quicker to look at. So let's go ahead and talk about how to balance ionic compounds that contain polyatomic ions. And we're just going to use the same methods that we used before, Now we're just using a group of atoms as one of our ions instead of just a single element. All right, so the first thing we're going to do is we're going to list the elements or ions in order so that the metal or the positively charged ion is listed first, right? And then I'm going to write the charges for those ions. And if those charges don't cancel each other out, then we're just going to have to continue to add ions in order to balance those charges. And so if I add another nitrate ion, so this polyatomic ion right here is nitrate, and we're trying to write the formula for calcium nitrate here. So if I add another one of those, then you can see that the charges are going to cancel out. I have 2 positive charges and 2 negative charges, so that equals 0. And so my formula here is CaNO3 2. And one other thing that I want to point out that's really important here is these parentheses that are around the nitrate polyatomic ion. The only time you need these is when you have a number that's larger than 1 that is behind that. Anytime you have more than 1 polyatomic ion in a formula, you have to have parentheses, and then the number that says how many of those ions you have goes right behind those parentheses. And you know, this is just really important to make sure that you include those, because you don't want it to look like you have, 32 oxygens, because you don't have 32 oxygens. You want your formula to reflect the correct information. All right, so now let's take a look at balancing ionic compounds with polyatomic ions using the crisscross method. So this is just like we did before. So I'm going to list my elements in order so that the metal or the positive ion is first, and then my polyatomic ion or my negatively charged ion is last. And I'm going to write down their charges, and I'm going to drop the sign, so goodbye to the positive and negative sign. And then I'm going to crisscross the numbers. Okay, and so in this case, because I'm going to have a 2 after that nitrate, remember I want to add my parentheses just so that I make sure I'm very clear that that's a group of atoms and that I have 2 groups of those atoms and not 32 oxygens. So let's go ahead and crisscross our numbers. And I did crisscross the one here just to show you that we're crisscrossing, but when we write our final formula, we never write a 1 as a subscript in a chemical formula. So remember that if we don't put the subscript, it's automatically understood that we have 1, and we included those parentheses, so CaNO3 2 would be our correct formula here. All right, so when we're writing balanced formulas for ionic compounds that contain transition metals, then we have to follow these rules. And the only difference here is that with a transition metal, we cannot look at the periodic table and determine the charge on that metal cation, right? And so we have to be given that information. And we're going to either be given that information in the form of Roman numerals in the name of the substance, or we have to be told what the charge on that metal ion is. All right, you can't look at the table, and even if you were to look it up online, sometimes there's many different, forms of or many different ways that 2 elements can come together. So in this case, this is iron 3 oxide. These Roman numerals here tell us that charge on iron is +3. And so now that we know the charge on iron, we can go ahead and balance out our charges and come up with a formula. So you can see it took 2 irons and 6 oxygens to come up with the formula here, Fe2O3. And if we were to just do the crisscross method, we would end up with the same answer, right? And then again, if you would need to reduce, then you would have to reduce, but in this case, we don't have to do any reducing. So let's go ahead, and I would like for you guys to pause the video and give this a try. See if you can write the balanced chemical formulas for these compounds right here. All right, so hopefully you were able to pause the video and come up with the balanced formulas here. So let's go ahead. We're starting with calcium chloride. So calcium is right here on our periodic table, and chlorine is right here. And calcium is a group 2 metal, so it's going to have a +2 charge, and chlorine is in group 7, so that's going to have a -1 charge. And if I were to crisscross those, I would end up with CaCl2. All right, so there's my formula for that one. Sodium nitride. Sodium is right here and nitrogen is right here. And so sodium is a group 1 metal, so it's going to have a +1 charge. And nitrogen is a group 5 nonmetal, so it's going to have a -3 charge. And if I just crisscross those, then I end up with Na3N. Sorry, my capital N's look like lowercase n's. I just try to make them taller. I know it always throws everybody off, but I feel weird writing them the other way. All right, potassium nitrate. I've got potassium here. It's a group 1 metal, so it's got a +1 charge. And nitrate is not the same as nitride. And we'll talk more about this when we talk about naming these. But nitrate is a polyatomic ion right here. And that is NO3 minus. And so we've got NO3 minus 1. And this is a +1 here. This is a -1 here. Those are equal and opposite. So I'm going to say they're going to cancel each other out. And my formula is going to be KNO3. And that's it. All right. You could do the crisscross thing. You don't have to. If you can recognize that they're equal and opposite in charge, then those charges just cancel each other out. And you end up with a compound with, the 1-to-1 ratio. All right. Magnesium hydroxide. Magnesium is right here. It's a group 2 metal, so it's got a +2 charge. And hydroxide is a polyatomic ion, so it's got an OH -1 charge. And if we crisscross those, I end up with MgOH in parentheses and then a 2. And that's my balanced formula for that. And then chromium 3 cyanide. So my biggest key here, or my biggest clue here, is these Roman numerals. And that means that I've got a transition metal, and I could have already determined that by looking at my periodic table. But remember, those Roman numerals tell me what the charge on this chromium atom is. So I've got chromium 3, and I know it's positive because chromium is a metal, and metals form positively charged ions. All right, and cyanide is a polyatomic ion, so I've got Cn here with a -1 charge. And if I crisscross those, I end up with chromium, cyanide with a 3 after it, CrCN3. All right, so hopefully this video was helpful. If you have any questions, go ahead and write them down and be ready to ask in class, and I will see you guys then. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.